Pluto, a far-flung and enigmatic world, was once a solitary and reliable planet within our solar system. However, recent discussions among leading astrophysicists, including Neil deGrasse Tyson and Michio Kaku, have thrust Pluto back into the limelight with surprising revelations. These scientists have proposed that Pluto's orbit may eventually intersect with Neptune's, a notion that raises questions about how such a collision might occur and what the consequences of such a cosmic event could be. Could this lead to a fascinating and unusual anomaly, or is there something more to this potential planetary collision? Join us as we delve into the possible outcomes of a Pluto-Neptune impact. Pluto, once considered a planet in its own right, is now relegated to a smaller category thanks to its unusual orbit and its status as a dwarf planet. Despite its demotion, Pluto remains a subject of fascination and research within the scientific community. Recent studies by leading astronomers show that Pluto's orbit is perilously close to Neptune's, raising alarms among astrophysicists like Tyson and Kaku about the possibility of a catastrophic collision between the two. But how could such a collision happen? Unlike the other planets in our solar system, Pluto follows an eccentric path around the Sun, taking an astonishing 248 years to complete one full orbit. Since its discovery in 1930, Pluto has not even finished a single orbit around the Sun. However, the intrigue surrounding Pluto does not end there. Its orbit is characterized by a highly elliptical shape, unlike the nearly circular orbits of the larger planets. What makes Pluto's orbit even more perplexing is its tilt. Pluto's orbit is tilted at an angle of 17 degrees to the plane of the solar system, which adds complexity to its orbital dynamics. This tilt, combined with its irregular shape, makes Pluto's orbit significantly more chaotic compared to the other planets. One of the most interesting aspects of Pluto's orbit is its interaction with Neptune's orbit. For approximately 20 years of each orbit, Pluto actually comes closer to the Sun than Neptune, which is contrary to what one might expect based on their positions within the solar system. This raises the natural question, why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets in the solar system. When Pluto's orbit was first studied after its discovery, astronomers struggled to understand its unusual trajectory. Unlike the orbits of other planets, which lie close to the ecliptic plane, Pluto's orbit stands out due to its steep tilt and elliptical shape. The mystery surrounding Pluto's orbit only deepened when it was found that, in the grand scheme of things, Pluto's orbit does indeed cross that of Neptune's. This apparent paradox is resolved by the complex gravitational dynamics of the solar system, specifically through a phenomenon known as the three-body problem. The three-body problem in astrophysics is a challenge of predicting the motion of three objects, like Pluto, Neptune, and the Sun, that influence each other through their gravitational forces. The interactions between these objects create a dynamic system that is difficult to predict, as each body affects the others in a constantly changing way. For Pluto, this three-body problem helps explain why its orbit is stable despite crossing Neptune's orbit. One key concept that keeps Pluto's orbit stable is libration. In the case of Pluto and Neptune, this term refers to the phenomenon where, whenever Pluto crosses Neptune's orbit, the two planets are always at least 90 degrees apart. This spatial separation is crucial in preventing the two bodies from colliding. Another important factor is degree libration, which refers to the vertical movement of a celestial body within its orbit. For Pluto, this means that when it comes close to Neptune or any other large planet, it remains situated well above or below the plane of their orbits, adding another layer of protection against potential collisions. A third concept that stabilizes Pluto's orbit is VZ wobbling, named after the three scientists Kale and O, who studied how celestial bodies move in space. This phenomenon refers to the way in which Pluto, Neptune, and the Sun influence each other through gravity, causing slight shifts in their positions over time. In Pluto's case, VZ wobbling helps explain why its orbit, despite seeming erratic, remains stable. These forces contribute to maintaining Pluto's orbit for incredibly long periods, possibly even billions of years. Although Pluto's orbit is chaotic in nature, these gravitational influences from other planets help keep its trajectory stable. In the broader context of the solar system, these forces play a vital role in preventing planets and other celestial bodies from crashing into one another. Without these stabilizing factors, the solar system would be a much more tumultuous place, with planets and dwarf planets potentially colliding or being ejected from their orbits, causing a cascading series of impacts. For Pluto, this is especially important, given the ongoing discussions about a potential collision with Neptune. Understanding Pluto's orbit gives us insight into the dynamic nature of the solar system. It serves as a reminder that even the most seemingly unstable orbits can achieve a state of equilibrium through the intricate dance of gravitational forces and orbital mechanics. The study of Pluto's orbit also highlights the need for continual research and observation to better understand the forces that shape our solar system. The case of Pluto illustrates the importance of studying the unpredictable nature of celestial bodies and the role that gravitational interactions play in their movements. The concept of orbital resonance, which refers to the delicate balance of gravitational forces that govern the orbits of celestial bodies, is clearly demonstrated by Pluto. Even small changes in its position or speed can dramatically alter its long-term orbit. In the late 1980s, computer simulations provided valuable insights into Pluto's orbit. These simulations showed that despite the stabilizing effects of phenomena like libration, Pluto's orbit can still be highly unpredictable. A tiny deviation in its initial conditions, such as its position or velocity, could result in dramatic differences in its path over the course of millions of years. Despite this inherent unpredictability, these models also showed that Pluto's orbit remains relatively stable over billions of years, suggesting that its journey around the Sun follows an underlying order, even if it appears chaotic. However, these simulations also reveal the challenges of making precise, long-term predictions. The three-body problem, combined with the sensitivity of the system to initial conditions, means that predicting Pluto's future trajectory is a complex and uncertain task. Although simulations provide a useful tool for understanding and forecasting the behavior of celestial bodies, they are limited by the precision of the initial data and the complexity of the forces at play. These challenges are underscored by the fact that large orbits, like Pluto's, tend to be turbulent and difficult to predict. The example of Pluto's orbit serves as a reminder of the ever-changing and dynamic nature of the universe. While we have made significant strides in understanding space, the case of Pluto demonstrates how much we still have to learn. The gravitational influences of the giant planets, such as Jupiter, Neptune, and Saturn, play a crucial role in shaping Pluto's orbit. Their presence and positions have far-reaching implications for the stability and trajectory of other bodies in the solar system. This brings us to the question, why are prominent astrophysicists like Neil deGrasse Tyson raising concerns about a potential impact between Pluto and Neptune? Despite all the complex forces working to prevent such a scenario, Tyson, a renowned astrophysicist who played a significant role in Pluto's reclassification from planet to dwarf planet, offers an insightful perspective on the evolving nature of celestial mechanics. Tyson argues that while Pluto's orbit is stable for now, it may undergo significant changes in the future. This possibility highlights how much more we still have to discover about the forces that govern our solar system. Tyson's views on Pluto's renaming and its current status as a dwarf planet are rooted in the ever-expanding understanding of our solar system. He believes that this reclassification is not a demotion, but rather a necessary adjustment in line with our increasing knowledge of the various bodies orbiting our Sun. His approach to celestial mechanics is one of ongoing learning and transformation. Tyson acknowledges the complexities of Pluto's orbit and its interactions with Neptune, while recognizing the inherent unpredictability of space. He suggests that while Pluto's orbit is stable at the moment, it could undergo significant changes in the future, serving as a reminder of the dynamic and ever-evolving nature of our understanding of the cosmos. Tyson's perspective highlights the inherent uncertainty in space exploration and celestial mechanics, underscoring the need for continuous study and adaptation in the face of new discoveries. He points out that even though Pluto's orbit has been relatively stable for billions of years, there is always the possibility of unforeseen changes as we learn more about the forces acting upon these distant bodies. The complexity of Pluto's relationship with Neptune is an excellent example of how even well-understood orbital dynamics can be subject to future alterations as our knowledge evolves. Furthermore, Tyson's observations on Pluto's orbital resonance with Neptune, where Pluto completes 2 orbits for every 3 of Neptune's, show how delicate and finely tuned the mechanics of the solar system are. This resonance helps maintain Pluto's stability by preventing it from coming into close proximity with Neptune, a crucial factor in the continued security of both planets. However, Tyson's concerns stem from the fact that such dynamic systems can still be vulnerable to changes, especially over long time scales. While the current trajectory of Pluto's orbit suggests that a collision with Neptune is highly improbable in the foreseeable future, Tyson reminds us that cosmic events and celestial movements are ongoing and nothing is set in stone. The broader implications of this idea are profound. Tyson suggests that the possibility of Pluto and Neptune's paths interacting in unexpected ways underscores the complexity and unpredictability of the universe. Even with all the forces working to keep these planetary orbits stable, there are always factors that could alter their courses. This recognition of uncertainty and dynamism is essential in the scientific study of space, as it drives ongoing research and technological advancements in the field of astrophysics. Understanding the mechanisms that keep planetary bodies in their orbits, as well as how they may shift over time, is critical to understanding the broader structure of the solar system and beyond. In addition, Tyson's involvement in the renaming of Pluto from a planet to a dwarf planet reflects the evolving nature of scientific classification. The decision was not based on a diminishment of Pluto's importance, but rather on a more nuanced understanding of what constitutes a planet. As our knowledge of the solar system has deepened, we have recognized that Pluto does not meet the criteria for a full-fledged planet, primarily due to its smaller size and irregular orbit. However, Pluto remains a fascinating object to study, providing insights into the outer reaches of the solar system and offering a window into the history of planetary formation and evolution. Michio Kaku, another renowned astrophysicist, shares similar sentiments regarding the complexities of Pluto's orbital dynamics. Kaku, known for his work on string theory and his ability to explain complex scientific concepts in an accessible manner, also emphasizes the need for ongoing exploration and study of the dynamic forces that govern celestial bodies like Pluto.